Welcome to this fascinating lecture on parasitology. Today, we are going to explore one of the most unexpected and remarkable creatures in the animal kingdom, the hood mockingbird. When we think of parasites, we usually imagine microscopic organisms, worms, or insects like ticks. We rarely picture a cute, singing bird on a sunny tropical island. But nature is full of surprises. In this session, we will discover how extreme environmental pressures, like severe droughts, can force a seemingly normal animal to adopt a parasitic lifestyle just to survive. Let us dive into the world of this tiny avian vampire. To begin our journey, let us understand why this bird is so unique. Most parasites we study in zoology are tiny, often microscopic, or creepy crawly insects. The hood mockingbird breaks this mold completely. It lives in an incredibly harsh environment where food and fresh water can vanish during severe droughts. Survival in such extreme conditions requires extreme measures. When this bird gets thirsty or hungry and cannot find water, it does not just give up. Instead, it seeks out larger animals and actually drinks their blood. This behavior makes it a perfect real-world example of how environmental stress drives extreme survival strategies. Now that we know what this bird does, let us look at its formal scientific classification. The hood mockingbird, scientifically known as Mimus macdonaldi, is endemic to Hispaniola Island in the Galapagos. In parasitology, we classify this bird as a facultative hematophagous parasite. Let us break those terms down. The word facultative is crucial here. It means the bird does not strictly need blood to survive under normal conditions. It usually eats insects and seeds. It only chooses to drink blood when conditions become too tough. The term hematophagous simply means blood eating, so it is an opportunistic vampire. Building on its classification, let us examine how this facultative hematophagy actually works in the wild. Mechanistically, the mockingbird targets much larger vertebrates that share its habitat, such as marine iguanas, Nazca boobies, and waved albatrosses. It is important to note that the bird does not act like a predator. It does not kill these animals. Instead, it acts as a true parasite. It carefully pecks at existing wounds, removes ticks, or targets soft tissues to draw blood. By doing this, it supplements its diet with vital fluids and nutrients, keeping itself alive without destroying its host. You might be wondering why a zoology student needs to study a blood-drinking bird. The answer lies in the evolution of parasitism itself. Most parasites we study have been evolving their traits for millions of years, making it very difficult to see how those behaviors originally started. The hood mockingbird provides a living, observable laboratory. With this bird, we are witnessing the very early evolutionary steps of parasitism happening right now. We can clearly see that this behavior is driven directly by environmental stress, specifically the extreme aridity and lack of fresh water on its island. Beyond evolution, studying this bird teaches us a vital lesson about host-parasite tolerance. Interestingly, the seabirds and marine iguanas often do not fight back when the mockingbirds peck at them. Why would a host allow this? It comes down to a delicate cost-benefit balance in nature. For a large iguana, the physical energy required to thrash around and fight off a persistent, agile little bird might actually be greater than the energy it loses from giving up a few drops of blood. It is an incredible example of biological economics in action. Now that we understand the biological context, let us look at the mathematics of this relationship. Parasitism is ultimately about the theft of energy. To truly understand the mockingbird's impact, ecologists use a bioenergetic model. This formula calculates the total parasitic energy extracted, denoted as EP. It equals N, the number of feeding visits, multiplied by V, the volume of blood per visit. We then multiply by rho B, which is the energy density of the host's blood, telling us how many joules are in 1 milliliter. Finally, we multiply by eta, the bird's assimilation efficiency, which measures how well its digestive system absorbs that energy. If the bird makes more visits or digests more efficiently, the total energy it steals increases proportionally. Let us apply this formula with a concrete example. Imagine a single hood mockingbird feeding on a resting Nazca booby. We are given that the bird makes 5 separate feeding visits, consuming 2 milliliters of blood each time. The booby's blood has an energy density of 4,000 joules per milliliter, and the bird's digestion efficiency is 80%, or 0.8. We need to find the total usable energy gained. First, we multiply 5 visits by 2 milliliters to get 10 milliliters of total blood consumed. Next, we multiply that 10 milliliters by the 4,000 joules per milliliter density, giving us 40,000 joules of raw energy. Finally, we multiply by the 0.8 efficiency. The final answer is 32,000 joules. This significant caloric boost is exactly what keeps the bird alive during a harsh, waterless day. Having seen what the bird gains, we must shift our perspective to the host. How much does the host actually lose? To find out, we use a slightly modified formula to calculate the total raw energy lost, which we call E-loss. This is simply the number of visits, N, multiplied by the volume per visit, V, and the energy density of the blood, rho B. Notice that the assimilation efficiency is missing here. Why? Because for the host, the bird's digestion efficiency does not matter at all. Once the blood is taken, that raw energy is lost to the host forever, regardless of how well the bird digests it. If a flock of birds attacks, the variable N increases rapidly, causing a massive spike in energy loss for the host. Let us see this host burden in action with a new example. Imagine a marine iguana during a severe drought. A flock of mockingbirds targets this iguana, making a total of 15 feeding visits. They take 1.5 milliliters of blood per visit, and the iguana's blood has an energy density of 3,500 joules per milliliter. We want to calculate the total raw energy lost by the iguana. We start by multiplying the 15 visits by the 1.5 milliliters per visit, which tells us the iguana lost 22.5 milliliters of blood in total. Next, we multiply that 22.5 milliliters by the energy density of 3,500 joules per milliliter. The final answer is 78,850 joules of raw energy lost. This is a massive amount of energy drained from a single animal. So we have calculated that the iguana lost 78,750 joules. But what does that number actually mean for the animal's survival? To understand the true ecological impact, we need to derive the percentage burden. We are given that this marine iguana has a total daily energy intake of 150,000 joules from eating algae. We want to establish exactly what fraction of its daily food intake was stolen by the parasites. To set this up, we use a simple ratio. The percentage burden is equal to the energy lost, E-loss, divided by the total daily intake, E-in, and then multiplied by 100 to convert it into a percentage. This mathematical setup will reveal the true severity of the parasitic relationship. Continuing our derivation, let us plug in the numbers to find the final result. We substitute our calculated energy loss of 78750 joules into the numerator and the daily intake of 150,000 joules into the denominator. Dividing 78750 by 1500 gives us exactly 0.525. Multiplying this decimal by 100 yields our final result, 52.5%. This is a profound physical interpretation. It proves mathematically that the marine iguana is losing more than half of its entire daily energy intake to these tiny birds. This clearly demonstrates how a seemingly harmless bird can impose a massive, life-threatening biological burden on its host during times of environmental stress. To bring all these concepts and mathematics together, let us look at this diagram illustrating the parasitic energy transfer. In the center, you see the large marine iguana resting on the rocks, acting as the host. Perched right on its back is the much smaller hood mockingbird. Notice the arrow pointing to the feeding site, where the bird is drawing blood. Connected to this interaction is a call-out box displaying our bioenergetic formula. EP equals N times V times rho B times eta. This visual perfectly summarizes the relationship. The physical act of the bird pecking the iguana directly translates into the mathematical extraction of energy. It shows us exactly how environmental aridity forces this incredible biological interaction. We have covered a lot of ground today, so let us review our key takeaways. First, we learned that the hood mockingbird is a remarkable facultative vertebrate parasite, proving that even beautiful songbirds can become vampires when necessary. Second, we saw that this behavior is driven entirely by extreme environmental aridity, offering a real-time look at the evolution of parasitism. Third, by using bioenergetic formulas, we successfully quantified both the life-saving energy the bird gains and the massive energetic burden it places on its host. Finally, this bird reminds us that parasitism is a highly effective universal survival strategy that can evolve in any branch of the animal kingdom when survival is on the line. Great job following along with the math and concepts today.